Okay, now we're going to have a look at torque, frequency, speed, and horsepower as they're affected by loading and unloading of these three-phase motors. Last class we looked at the rotating magnetic fields in the three-phase stator. The rate in which the stator field rotating is called the synchronous speed. Now we determine that by the number of poles and the applied frequency. We have the calculation here where the speed is going to equal 120 times the frequency divided by poles per phase, as shown here. All these three-phase motors have either 2, 4, 6, 8, 10, or 12 poles. First, let's have a look at motor torque. Now, torque is the rotational or twisting force of the motor. The three factors that determine the amount of torque produced by a motor are the strength of the magnetic field of the stator, the strength of the rotor magnetic field, the phase angle between the stator magnetic field and the rotor magnetic field. Now we have this equation here we look at and reference when we try to understand what the effects of changing of the stator field, the rotor field, and the power factor, or the phase angle between the two fields, what effect they have on torque. So when we look here, we have our torque equals K. This is just a constant. It's an aggregate of values that don't change as the load increases and decreases for the motor. We have the stator flux here, okay, and that's going to be influenced by the increase and decrease of current in the rotor. And we have the rotor current here. That rotor current is going to determine the strength of the rotor flux. And then we have the power factor of the rotor here. And we're going to look at what relationship the rotor power factor has with the phase angle between the stator and the rotor magnetic field. At the instant of startup, the rotor is at 0 RPM, which means we have 100% slip, and the slip speed would be 1800 RPM. If you don't remember, the slip is the difference between synchronous speed and rotor speed. At this point, the voltage induced in the rotor will be at its maximum. Okay, and you remember the E generated is BLV, where B is the magnetic field strength, L is the length of the conductors, and V is the velocity of the rotating magnetic field in this example, or in a three-phase motor. Now also the frequency will be the same at this point as the stator frequency. Okay, so the rotor frequency is 0 RPM. It's going to have 60 hertz and the maximum voltage across it. Now at this point also, there's very little opposition to current flow in the rotor circuit. The current will be very high, which will create a very strong magnetic field around the rotor bars. Now also, because the rotor current at this point is so high, it will cause the stator current to be high. It will perform exactly like a normal transformer. If you add load onto the secondary of a transformer, the current's going to go up on your secondary, which is going to make the current go up on your primary. Same thing happens in a standard induction motor. Okay, and as it says here, it acts like a static transformer. Now this large increase in current is what we call inrush current. Now we had a look at this picture in one of the previous videos showing the rotor force going in a clockwise direction and how it interacts with the rotating flux field of the stator. Okay, so at startup, that high inrush current and that high current going through the rotor bars, because the high induced voltage is going to have a significant effect on the strength of the magnetic field of the stator and the strength of the magnetic field of the rotor. So at startup, the conductor currents in the rotor and the stator create a strong magnetic fields, and that interaction of those magnetic fields produces a high amount of startup torque. Okay, let's put torque on hold for a second and have a look at rotor frequency. Last class and the last videos, we looked at rotor frequency. Rotor frequency is proportional, as it says here, to the amount of slip there is in a motor. If the motor is not rotating and the stator is energized, the rotor frequency will be the same as the supply frequency. Okay? As the rotor accelerates to full speed, the frequency of the rotor will decrease. So in this example here, if we have a 4-pole motor, its synchronous speed is going to be 1800 RPM. Okay, so if we use that same formula to calculate synchronous speed to find out what the frequency will be of the rotor, we can calculate it by finding the frequency will be the number of poles multiplied by the slip speed of the rotor, okay, or the slip RPM. And then we divide it by our 120, which is a function of 2 poles times 60 cycles a second. So we can convert revolutions per minute to seconds. So now if we have our 1800 RPM motor and our rotor is not rotating yet, its slip speed will be the same as the synchronous speed, which is 1800 RPM. So when we calculate that out, we're going to calculate the frequency of the rotor will be 60 hertz, the same as the applied voltage. Now, when the rotor, let's say its full load RPM for the motor is 1750 RPM, well, if we do the same calculation, but now the slip RPM is going to be the difference between the synchronous speed and the actual rotor speed, which works out to, if it's 750 rotor speed, we have 50 RPM. So when we multiply 4 times 50 gives us 200 divided by 120. The new rotor frequency is going to be 1.666 repeating hertz. Okay, a lot smaller. So when the rotor is up to full speed or near full speed, the frequency in the rotor is way down. Now, because of this slip frequency relationship, we can state that the rotor frequency is directly proportional to the slip, or the percentage of the slip times the supply frequency will equal the rotor frequency. Okay, so if the percent slip is calculated by 1800, for this example, 1800 minus 1750, then we divide it by our synchronous speed of 1800, gives us a 2.77% slip. Now, if we just multiply 2.77 times 60 hertz, we're going to have that 1.6 repeating frequency for a rotor. So they're directly proportional to each other. Here we have a great illustration showing us the effect of the rotor speed has on the frequency and voltage in the rotor. So here at one end, we have the starting point where the rotor would be 0 RPM. The voltage across the rotor from 0 to peak here will be, as you can see, its highest. As the rotor accelerates, our voltage, it's going to decrease. And also, if you look at the period here for the waveform, it's getting longer and longer. So our frequency will be decreasing at the same time. So eventually it's going to start getting a smaller and smaller frequency and a lower and lower voltage until it gets up to full speed, or the rotor will be at its maximum RPM. So now let's have a look at the phase angle difference between the stator magnetic field and the rotor magnetic field. Okay, that's the third thing that affects motor torque. Now imagine two bar magnets connected together. The force necessary to pull them apart is determined by the strength of the magnetic field and the angle of the coupling. In this example, there's no angle of coupling. So this would represent the two magnetic fields that we would say are in phase with each other. Okay, so the force to pull these apart if these magnets were moved apart at an angle, like shown in the picture here, the coupling force between them would be much less. So the amount of force necessary to pull two magnets apart now is dependent on the strength of each magnet and the coupling angle. The greater the angle between the two magnets, the less force necessary to pull them apart. This represents an out-of-phase condition between the rotor magnetic field and the stator magnetic field. So right now, let's have a look at the power factor of the rotor. The rotor is an inductive load, so it will have a power factor. Okay, so the power factor of the rotor is determined by the inductive reactance in the rotor, which is determined by the inductance and the frequency in the rotor, where an AC motor, the inductance stays constant, but the frequency can vary with these motors. And as the frequency rises, the XL will follow, increasing and decreasing the power factor. So if you guys remember from last year, when you were calculating inductance reactance, it was a 2 pi FL. So we have 2 pi, and we had our frequency here, and then we had our inductance. Okay, in the rotor, our inductance is fixed. But as we were discussing before, as we accelerate and decelerate, our frequency changes. Okay, so it's safe to conclude that our inductive reactance will change as the speed of the rotor increases. Remember, when the speed of the rotor goes from 0 RPM all the way to full RPM, the frequency is dropping down significantly. So in that previous example, at startup, the frequency was 60 hertz. Now, all the way up to full speed, where it got down to 1.6 hertz. Okay, that 1.6 and that change in frequency will have a significant effect on our rotor power factor. Okay, and then if we have a look down here, our original formula we're trying to look at, we can look at the strength of the stator field, the current in the rotor field. But here's that power factor of the rotor we're going to look at. Okay, so the rotor power factor and the stator to rotor flux relationship are pretty critical to understand how speed of the rotor is going to affect the torque. So we already see how the inductive reactance in the rotor is going to be affected by the change in frequency in the rotor. Okay, so as the frequency increases or decreases, the inductive reactance is going to follow. So as the frequency decreases, our inductive reactance is going to decrease. So it's safe to conclude that as the rotor accelerates to full speed, our power factor in our rotor should improve. Okay, how that connects with the stator to rotor flux phase relationship is when we look at our induced rotor voltage and our power factor angle here, how it's leading our rotor current. Our rotor current is lagging our induced voltage. This induced rotor voltage is in phase with the magnetic field that's inducing it, which is the stator flux. Okay, so we have our stator flux here, and it's in phase with our induced rotor voltage. Now, our power factor angle is going to tell us how far out of phase our rotor current is to our induced rotor voltage. Well, our rotor current is in phase with our rotor flux. Okay, so we can safely conclude here that the stator flux, the angle between the flux and the rotor, is going to be the same angular relationship as the power factor in the rotor. So let's say at startup, it can get to as low as 15% power factor, really, really low. And then as it accelerates, the angle decreases here, and our angle between our rotor flux and our stator flux gets closer and closer, and then our amount of torque we have on our motor will be increasing. So when we look at our torque formula here again, where our, again, constant times our stator flux times our rotor current times our power factor, we can see that how the power factor is going to affect the amount of torque our motor is going to be putting out. So as our motor accelerates, our frequency is going to go down. It's going to reduce. Our inductive reactance is going to go down. Our power factor will go down, which is going to mean our torque is going to go up. Okay? And then the opposite is true. As the frequency increases in our rotor, our inductive reactance will go up, and our power factor will go up also, which will reduce our torque, which has a small amount to play with. So when we look at rotor/motor accelerating, the rotor magnetic field is pushing and pulling the rotor stator, causing it to rotate. This is when torque is produced. As the RPM of the rotor increases, the percent slip's going to decrease. Also, the induced voltage decreases and the rotor frequency decreases. Okay, and then the rotor power factor decreases. So, because the relative velocity between the rotating field and the rotating rotor is decreasing, slip is decreasing. The induced voltage is reducing. Again, that E generated is BLV. The V is decreasing. Okay, so our induced voltage in our rotor is going to decrease. Also, since the rotor speed is increasing at a rate in which the flux of the stator is cutting the rotor conductors is less, the rotor frequency will reduce. Okay, so this is what's happening when we're going from 0 or 1 all the way up to, let's say, 1797 in this example is would be the no load RPM of these particular. So here we have our motor at full no load speed. So there's no load or no resistance rotation, or what we also call it counter torque on the motor shaft, or very little. The rotor is at full no load speed. The speed is just enough to maintain enough induced voltage to keep the rotor turning. The only resistance at this point will be windage and some mechanical resistances in the bearings. Sometimes for an 1800 RPM motor, you could see this getting up to 1798.5 RPM, like almost rate to synchronous speed. Now, when we have no load, the RPM of the rotor will be at its maximum. Okay, the percent slip will be at the lowest. Okay, the induced voltage is at its lowest. The rotor frequency will be at its lowest. The rotor power factor percent is at its highest. Okay, so it's going to be close to, whatever the maximum power factor would be. Could be in the high 90 percentile range. A motor that is at 1797 has a synchronous speed of 1800 RPM. It will have the slip speed of 3 RPM and a percent slip of 0.0166%. So that's a really, really small amount of slip. Okay, and we calculate it as such. So when we look at what the rotor frequency is going to be, it's dropped down to 1 hertz, or 0.166% times 60 hertz. So as we add load to the motor, the speed is going to change. So for this example, let's assume full load speed is going to be 1750 RPM. So what that means is when we add mechanical load to the motor, it's going to decelerate from its no load speed down to its full load speed. Okay, now we'll go through some of the reasons for that in a moment. So when load is put on the motor, it's going to start to decelerate the rotation of the shaft. That means the percent slip is going to increase. Okay, the slip speed is going to increase also. The induced voltage now, because of that, is going to increase because we have our rotating stator flux with a relative velocity to the rotor is increasing. The rotor is slowing down, so we're going to be cutting the rotor bars more often. So the induced voltage will increase. Now, the rotor current, because of that increase in voltage, will go up. Okay, that rotor current increasing because of the transformer effect, what we discussed before, will cause the stator current to increase. And then that stator current increases, so our stator flux will increase. Okay, so you see there's all these things going up. The rotor field strength is increasing because the rotor current increases. Those together are going to cause our torque to increase. Now, at this point, there's a very slight increase in frequency, okay, which is going to slightly increase our power factor, but at this point, not quite significant enough to have an overall negative effect on our torque. Okay, so now because the relative velocity, the key point here, between the rotating stator field and the rotating rotor is increasing, slip is increasing, the induced voltage in the rotor increases. Okay, so we're going to have our E generated is going to go up. Okay. Now, the speed recovers, but just enough to maintain torque to handle the increased load. It won't keep, this will only keep going through its cycle till it hits a equilibrium. So if we look down here at the bottom, when our load increases, our load goes up here, our RPM is going to decrease, which makes our slip go up. When our slip goes up, our induced rotor voltage is going to go up, which means our rotor current is going to go up. Our rotor current is going to make our rotor flux go up, which is going to interact with our increased stator flux, which is going to make our torque go up. And then our RPM will increase just enough to maintain that added torque. Now, when load is removed from the motor, again, let's assume the RPM, full load RPM is 1750. Now the opposite happens. Okay, so when load is removed, the RPM of the motor is going to jump up, is going to increase. The percent slip is going to decrease. Our induced voltage is going to decrease. So everything that happened as we added load to the motor is going to happen in the opposite. The current is going to decrease in the rotor. The field is going to weaken. The torque decreases. The rotor speed will return to the no load speed. Okay, again, has to do with the relative velocity between the rotor stator and the rotating rotor. Now if we have a look at our little diagram down here, our little chart, when our load goes down, RPM will go up, slip will go down, current in our rotor goes down, our flux in our rotor drops down, our torque will go down, our RPM will slow down. Because if you instantaneously take all load off of the 1750 RPM motor, it's going to jump up in speed. It's going to bounce up and then it's going to stabilize. It's going to find that equilibrium again. Now, what happens if we overload the motor? So let's say the motor gets up to full load and then we double the load on the motor. Okay, when the motor gets overloaded, the RPM of the rotor will decrease more. The percent slip will increase. The induced rotor voltage will increase. The rotor current increases, and the rotor field strength increases. And the torque will increase, and the rotor frequency will increase, and the rotor power factor will increase. So when we're looking at overloading a motor, this condition is basically more load than the motor can handle. Okay, more than it's designed to handle. So the increase in the rotor voltage and the rotor current causes the stator current to rise to a point where it should trigger its overload protection. This is what the overloads that we put in our motor circuits are looking for. They're looking for that abnormally high, well, when you get down to it, rotor current. Okay, so the rotor current's going to go really high to try and overcome that overload condition. But if the load is too high, it's not, that increase in torque is not going to be enough to get that motor up to full load speed. Now, if the increase in load is more than the generated torque can handle, the motor will stall, and the resulting current can get up to 6 times the FLA or for full load current, and can cause quite a violent electrical fault. Okay, so this is very unlikely because we always have overloads on our equipment. Now, on occasion, you may encounter someone who may size the overload incorrectly, and you can get this fault condition happen where it's going to go into what we call a locked rotor state. Okay, and it will it can cause a very violent electrical fault. So if we look at this graph here, this graph is showing us what the relationship between the speed of the rotor is and the torque. Okay, so when we look at this bottom, it's the synchronous speed here, so 100%, and what percent the rotor is of synchronous speed. Okay, so over at this end, this is at 0 RPM of the rotor. Okay, and then as we increase the speed here up to full speed of the rotor, we see at the 100%. When we look on the left here, it says full load torque. So this is basically 100% full load torque. So when we're fully loaded our motor, that's going to be at this point. And then it perfectly lines up with typically the 3 to 4.5% slip point. Okay, so when our motor is at 3 to 4.5% slip, typically it's at about 100% full load, or when it's at 100% full load, we can see 3 to 4.5% slip. Okay, but what we need to notice over here at this side is at 0 RPM, now we have that inrush current and that high current in our rotor. Okay, at 0 RPM, those two high currents are going to cause our torque to be 150% of our full load torque. Now this is just this one type of design. With different rotor designs, which I'm going to look at in another video, this starting point here is going to be a little different, and then the curve here is going to be a little different. So here we have our starting torque, which is about 150% at 0 RPM. As it accelerates, right, we have our power factor is reducing. Okay, and our voltage is reducing. Okay, our induced voltage in our rotor is reducing. So as it starts to go accelerate the rotor, our induced voltage is dropping, our power factor is dropping, so our power factor is dropping more than our induced voltage. So that angle of improved power factor is why we have an increase of torque at this point, all the way up to the, I'd say it's 20 to 25% slip point is usually where it's at. And then once we get up to this point here, our power factor, it gets quite good, and our rotor voltage gets quite low, and then now our actual available torque drops really low here now till we get to a full load, or as you notice way down here when we were at 0.5% slip, we're typically using 25% of full load torque. Okay. Now, the opposite holds true. When we have our motor running at full load here and we overload it, the rotor's going to slow down. The voltage is going to increase. Induced voltage in the rotor is going to increase, which is going to increase our amount of torque. That's going to keep going all the way up to this point. Now at this point here, our power factor starts getting really poor, and then all of a sudden it drops, and then it just, well, actually it'll most likely just drop right down to zero at this breakover point. This is called our breakover torque. Now, to look at motor torque here, we can calculate the actual foot-pound value for the torque if we know the horsepower of the motor and the actual running RPM of the motor, the shaft output RPM. Okay, by punching those numbers into this equation here. So if we have our torque is equal to our horsepower, and then 52 is a constant we use for converting horsepower and speed to torque. Okay, it's good to remember this. So when we have our horsepower, whichever it was our multiplied by 52 divided by the RPM of the motor. So when we look at that, our torque is going to be in foot-pounds, horsepower is going to be the output horsepower of the motor, and it's going to be the operational RPM of the motor. And then again, 52 is just a constant. So if we had a 20 horsepower motor that was running at 1775 RPM, okay, at full load, it will have an output torque of 59.178 foot-pounds. Okay. Now we can transpose the formula to find out if an occasion existed, which is I've never encountered. Horsepower is going to equal the amount of torque times the RPM of the motor. Then we divide that product by 52, our constant, and it actually is a way of calculating the horsepower. Okay, and where that'll come in is engineers are going to use that for sizing motors. If they have a piece of equipment that needs a certain amount of foot-pounds of force to turn it, they'll use this equation to try and calculate what size of electrical motor they're going to need. Now also, we have a metric equivalent here. Okay, so we have the torque is going to be in Newton meters. The output power of the motor will be in watts, and this is common in European and Asian motors, sizing them this way. And N is the operation RPM of the motor. Okay, and then that 9.5488, it's just a constant we use. Okay, don't really have to remember this for anything you might encounter on Friday. The previous one might be a good idea to pay attention to, where we use the imperial foot-pound units. So the same 20 horsepower motor at 1775 RPM, okay, at full load will have an output torque of, do the math, put the numbers into the equation, it's going to give us 80.26 Newton meters. Then also, if you wanted to or needed to calculate how much watts of a motor, output watts of a motor you need to drive 80.26 Newton meters, let's say for this example, of force, you can transpose the same formula. Very similar to what we did with the imperial units on the previous slide. Okay, one of the last things we're going to look at now is motor efficiency. You're going to spend some time going over motor efficiency in DC machines. I'll just get you through a little bit of this. No motor is perfectly efficient, as we all know. They all take more kilowatts in than they put out. That's with all electrical equipment. You look at a generator, which we're going to look at alternators later on this week. The amount of mechanical energy going into a generator is way higher than the output watts that we're sending out. Those output watts, electrical watts, go into this motor. They're going to be a lot higher than the mechanical output on the motor shaft. Okay, so when we're looking at efficiency, it's a relationship of the output power over the input power. Now the input power here, right, the output power is the total input power minus all the copper and stray power losses. Okay, so copper losses are going to be resistance and some eddy current losses, and then stray power losses are going to be heat and frictional losses, okay, in the motor. Now, input power, well, we know what input power, that's what's doing the work, that's what's going in on the electrical side. Output power, that's the horsepower, that's the mechanical output power we have. So when we have a 10 horsepower motor here in this example, and the 10 horsepower is the mechanical output at the motor shaft, when we convert that to watts, if we want to understand what the efficiency would be of this motor, if the 10 horsepower motor was 600 volts and 8.15 FLA, power factor of 90%, the input power to that motor would be 7622.8 watts. To find the efficiency, it's just a matter of dividing our output power, our 7,460 watts, divided by our 7622.8. That's going to give us a 97.8% efficient losses. So the total power losses in that situation will be 162.8 watts of losses. Thank you very much. I hope you found this informative.